Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about the moon, slowly, without hurrying. Of all the objects in the sky, the moon is the one that gives the unaided eye the most to work with, and the only one that shows a shape that changes and a surface that can be read night after night without any instrument at all. The sun is too bright to look at. The planets remain points of light no matter how carefully they are watched, and the stars hold their patterns unchanged across a human lifetime. But the moon presents a visible disk, roughly half a degree across, mottled with light and dark, sliding eastward against the fixed stars at a rate that can be followed from 1 hour to the next by anyone patient enough to note where it stands relative to a nearby star. Everything that was known about the moon before the 17th century came from watching in exactly this way, with the eye alone and with whatever means were available for recording what had been seen. The most obvious of its behaviors is the cycle of phases, and it repeats with enough regularity that it became the earliest reliable unit of timekeeping, longer than a day. A thin crescent appears low in the west after sunset, its horns pointing away from the place where the sun went down, and it sets soon after the twilight fades. On each following evening, it stands higher and thicker, until about a week after its first appearance, it shows a half-lit disk, the straight edge of the illuminated portion facing the sun, and it is then high in the southern sky at sunset for observers in the northern latitudes. The lit portion continues to swell, the boundary between light and dark bowing outward into an oval, and roughly 2 weeks after that first crescent, the moon rises in the east as the sun sets in the west, fully lit, round and bright enough to cast shadows and to wash the faintest stars out of the sky. Then the sequence reverses, the disk thinning from the other side, rising later each night, until it is a waning crescent visible in the eastern sky before dawn, and finally it is lost in the sun's glare for a day or two before the cycle begins again. The interval from one new moon to the next averages a little more than 29.5 days, and this is the length that calendars built on lunar months have had to accommodate, since a month cannot contain half a day and so must alternate between 29 and 30. That figure is not the time the moon takes to complete a circuit of the sky against the stars, which is shorter, about 27.33 days. The difference arises because the sun is also moving eastward among the stars over the course of a year, so that after the moon has returned to the same position relative to the background stars, it must travel a little further to catch up with the sun again and repeat the same phase. Both intervals can be measured without instruments, one by watching the phases and the other by watching which stars the moon passes. And the fact that they differ and the amount by which they differ was established by observers working with nothing more than a clear horizon and a long memory. The phases themselves reveal the geometry, though it took a long time and some argument for that reading to be secured. The lit portion always faces the sun, whether the sun is below the horizon or, in the case of a moon seen in daylight, plainly visible in another part of the sky. And the curved boundary of the lit region behaves exactly as the shadow line on a sphere would behave when the sphere is lit from one side and viewed from a changing angle. When the moon is a thin crescent, low in the twilight, the unlit part of the disk can often be made out as a dull grey circle completing the shape, faintly luminous, and this glow comes from sunlight that has struck the Earth and been reflected onto the lunar night side. It is a subtle effect, easily missed, and it is best seen when the crescent is slender and the sky is dark enough to give contrast without the moon itself being high and bright. Alongside the phases, there is the slow drift of the moon among the constellations, which is the fastest apparent motion of any body in the sky, apart from those produced by the Earth's own rotation. In the course of a single hour, the moon shifts eastward by roughly its own apparent width, which means that a star close to its limb early in the evening may be an appreciable distance away by the time the night is over. And occasionally the moon passes directly in front of a star and blots it out, the star vanishing without warning at the leading edge and reappearing later at the trailing one. These occultations are visible to the unaided eye when the star is bright, and they are abrupt, since the moon has no atmosphere to dim the star gradually. Though that conclusion belongs to a much later stage of the investigation. Over a day, the moon moves about 13 degrees eastward, which is why it rises later each night, on average by something near 50 minutes, and why the same phase never appears among the same stars from one month to the next in quite the same way. The path the moon follows through the constellations lies close to the path of the sun, but not exactly on it. The moon's track is tilted by about 5 degrees, so that in the course of each circuit it crosses the sun's path twice, once going north and once going south, and between those crossings it wanders a little above or below the line the sun follows. This is why the moon keeps to the same band of constellations that the sun and the planets occupy, and why eclipses are not monthly events, since a new moon or a full moon must fall near one of those crossing points for the three bodies to be aligned closely enough for a shadow to fall. The tilt also means that the highest and lowest points of the moon's monthly track shift over a longer cycle of about 19 years as the crossing points themselves creep slowly westward around the sky, and the extremes of moonrise position along the horizon vary accordingly from one year to the next. Observers who watched the horizon carefully over decades could and did notice this. The other thing the eye can see is the pattern on the disk itself, which is fixed. The moon shows dark grey patches of irregular shape set against a lighter, brighter background, and those patches occupy the same positions on the disk every month and every year, so that the face presented at one full moon is the face presented at the next. This is not what would be expected of a body turning freely, and it follows from the moon keeping one hemisphere permanently towards the Earth, its rotation matched to its orbit. The pattern is large enough and definite enough that cultures across the world have named the shapes they saw in it. A figure of a man, a hare or rabbit, a woman carrying a burden, and these readings differ, as readings of an ambiguous pattern will, but they all rest on the same underlying fact that the pattern does not change. The dark regions were later found to be low plains of dark volcanic rock, and the bright regions rugged highlands. But with the eye alone, all that can be established is that the contrast exists, that it is permanent, and that the boundaries between light and dark are irregular rather than geometric. The face is not, in the strictest sense, entirely fixed. The moon rocks slightly north and south and east and west, over the course of a month, because its orbit is not a perfect circle and its axis is not perfectly perpendicular to that orbit, so that the apparent center of the disk shifts a little back and forth, and features near the edge move in and out of view. The effect is small, a matter of a few degrees, and detecting it by eye alone is difficult, though its consequence is that rather more than half of the lunar surface can eventually be seen from the Earth, close to 3/5 of it, while a portion on the far side remains permanently hidden. Everything beyond that had to wait for glass, and much later for machines. What the eye could establish about the moon was, for a very long time, all that anyone had. And out of that limited material, a great deal was made, because the moon's behavior is regular enough to be tabulated and irregular enough to make the tabulating a serious undertaking. The basic difficulty is arithmetic. The interval from one new moon to the next, the synodic month, runs to a little over 29.5 days, which means that no whole number of days fits a month, and no whole number of months fits a year, since 12 synodic months fall about 11 days short of the time the sun takes to return to the same place among the stars. A calendar built on the moon will therefore drift against the seasons, and a calendar built on the seasons will lose track of the moon, and every literate society that tried to keep both in view had to invent some means of reconciling them. The means chosen differed from place to place, and the choices tell us a good deal about what each society wanted its calendar to do. The most detailed early record comes from Mesopotamia, written in cuneiform on clay, and its survival is partly a matter of the material, since clay tablets discarded in rubbish or buried in collapsed buildings endure in a way that papyrus does not. Babylonian months began with the evening on which the thin crescent was first seen after conjunction, a rule that ties the calendar directly to observation and to the weather, because a clouded western horizon can hide a crescent that is certainly there, since a month so defined lasts either 29 or 30 days, and since the moon does not alternate between the two in any simple pattern, the length of the coming month was a practical question, and much of the surviving material is concerned with answering it in advance. 12 such months made an ordinary year, and when the seasons had slipped too far, a 13th month was inserted, at first by decision and later according to a fixed scheme, so that the barley harvest and the festivals attached to it stayed roughly where they belonged. Alongside the calendar, there developed a habit of writing down what the sky had done. Scribes kept nightly records of the moon's position relative to particular stars, of the intervals between sunset and moonset around full moon, of eclipses both lunar and solar, and of a range of other phenomena including the weather and the price of barley, and these day-by-day accounts, kept over centuries, accumulated into a body of data unlike anything else in the ancient world. There were also long compilations of celestial omens, in which the appearance of the moon was read as a sign bearing on the fate of the king and the land. And it is worth noting that the omen tradition and the observational tradition supported one another, since a sign cannot be read reliably unless its appearances are known, and the desire to know when an eclipse might threaten the king was among the strongest motives for learning when eclipses come. Out of the archive came patterns. Eclipses do not occur at every full and new moon, because the moon's path is tilted with respect to the sun's, and they cluster instead in seasons separated by rather less than half a year when the crossing points of the two paths lie in the right direction. Babylonian astronomers established that the whole arrangement repeats after an interval of 223 synodic months, close to 18 years and 11 days, and they used this period to lay out schemes of possible eclipse dates far in advance, arranging the months in columns so that an eclipse possibility in one row implied another 18 years later. For lunar eclipses, this worked well, since a lunar eclipse is visible from the whole night side of the Earth, and a prediction can be checked. For solar eclipses, it was less satisfactory, because the shadow of the moon touches only a narrow track, and an eclipse correctly predicted as possible may be invisible from Babylon altogether. So the tablets speak of watching and sometimes record that the expected eclipse passed by. In the later centuries of the tradition, the arithmetic became more ambitious. Rather than simply repeating a period, scribes wrote out tables in which the varying speed of the moon, the length of each month, the position of the sun, and the timing of first crescent were computed step by step from column to column, each column advancing by a rule of its own. And from these tables, the phenomena of a whole year could be derived without any observation at all. The value they used for the mean length of the synodic month agrees with the modern figure to within a second or two, which is not the result of any single measurement, but of comparing eclipses separated by many centuries, since dividing a long interval by the number of months it contains spreads any error in the endpoints very thin. The archive itself was the instrument. Egypt took the other road. The civil calendar there consisted of 12 months of 30 days each, divided into 3 10-day weeks, with 5 additional days appended at the end, giving a year of 365 days exactly and no adjustment of any kind. Such a year is about a quarter of a day short, so it slips forward against the seasons by roughly 1 day in 4 years. And the whole cycle of slippage takes something over 1,400 years to come round, which means that a fixed civil date will over a long reign migrate slowly through spring, winter, autumn, and summer. The administrative convenience of a calendar with no intercalation is considerable, since intervals between dates can be counted without exception or dispute, and the Egyptian scheme was later admired and borrowed for exactly that reason by astronomers who wanted a uniform count of days. The moon was not thereby ignored. Alongside the civil year, the temples kept a lunar reckoning for services and festivals, with months determined by the moon's appearance, and the two systems ran in parallel, the one fixed and artificial, the other observational and irregular. In China, the lunisolar arrangement was pursued with unusual persistence, and the calendar became a matter of state, its computation and promulgation a duty of the court, and its accuracy a reflection on the legitimacy of the reigning house. Months began at conjunction rather than at first sighting of the crescent, which requires calculation rather than mere watching. And intercalary months were inserted according to their relation to the divisions of the solar year, so that the seasonal markers stayed within their proper months. Successive dynasties commissioned new calendrical systems when the old ones drifted, and the reform of the calendar became a recurring scholarly enterprise stretching across many centuries. Along with the calendars came records, eclipses noted in dynastic annals and in earlier chronicles, lunar eclipses among the inscriptions of the Shang oracle bones, and solar eclipses listed in the annals of the spring and autumn period, forming a series of dated observations that modern astronomers still consult when they need to know how the Earth's rotation has varied over the long term. The Greeks came to the problem later, and with a different emphasis. Their city calendars were lunar and locally managed, so that the month names and the intercalations of one city need not agree with those of its neighbor, an inconvenience for historians then and since. For farming and for the seasons, they relied on the risings and settings of bright stars, tabulated in almanacs that paired stellar events with weather expectations. The reconciliation of moon and sun was addressed by the observation associated with an Athenian astronomer of the 5th century before the Common Era and known independently in Babylon, that 19 solar years contain very nearly 235 synodic months, so that a cycle of 19 years with 7 intercalary months keeps the two in step for a long time. Greek natural philosophy contributed something else as well, an explanation rather than a rule, in the recognition that a lunar eclipse is the moon passing into the shadow the Earth casts, and a solar eclipse the moon passing in front of the sun. Later, Greek astronomers gained access to the Babylonian eclipse records, adopted the Egyptian fixed year for reckoning intervals, and set the beginning of their count of years in the middle of the 8th century before the Common Era, from which point onward a continuous chain of dated eclipses could be laid out and used. What the Greeks added to the accumulated tablets and annals was the idea that the distance and the size of the moon were quantities capable of being determined, not merely wondered at, and that the instrument for determining them was geometry applied to observations that anyone might make. The moon was the natural first subject for such an attempt, because it is the one celestial body near enough for its position against the stars to differ appreciably according to where on Earth the observer stands. That shift, which astronomers call parallax, amounts for the moon to a little less than a degree between an observer who sees it on the horizon and an imagined observer at the center of the Earth, which is small but not hopelessly small, and which lies within reach of careful naked eye measurement. For the sun, the corresponding shift is a matter of a few seconds of arc, far beyond anything the ancients could detect, and this difference in accessibility shaped the whole history of the subject, since the moon's distance was settled to within a few percent many centuries before the sun's was known at all. The earliest surviving attempt at a numerical treatment belongs to Aristarchus of Samos, working in the 3rd century before the Common Era, in a short treatise on the sizes and distances of the sun and moon. One of his methods rested on the moment of exact half-illumination, when the sun, the moon, and the Earth stand at the corners of a right angle, the right angle being at the moon. If the sun were infinitely far away, the elongation of the moon from the sun at that instant would be exactly 90 degrees. Because the sun is at a finite distance, the angle is slightly less, and the shortfall gives the ratio of the two distances. Aristarchus adopted a value of 87 degrees and concluded that the sun lies some 18 to 20 times farther than the moon. The reasoning is sound and the answer is wrong, because the true shortfall is only about 1/6 of a degree, and the true ratio is nearer 400, and because the instant of exact half-illumination cannot be judged with anything like the required precision. His second method used the geometry of a lunar eclipse and was far more successful in principle. When the moon enters the Earth's shadow, the width of that shadow at the moon's distance can be inferred from how long the moon takes to cross it, compared with how long it takes to cross its own diameter, and since the shadow is a cone tapering away from the Earth, the comparison yields a relation among the sizes of Earth, Moon, and Sun. Aristarchus concluded that the Moon's diameter is a substantial fraction of the Earth's, roughly a third, by the values that come out of his figures, which is of the right order and somewhat too large, the true ratio being a little more than a quarter. Later writers, having better eclipse timings and a better treatment of the shadow's taper, brought the ratio down towards its correct value. All such results were ratios expressed in Earth radii or Earth diameters, and to convert them into ordinary units, one needed the size of the Earth itself. That was supplied in the same century by Eratosthenes, who compared the noon altitude of the Sun at two places on nearly the same meridian, and derived a circumference in stadia. The figure has been much discussed, chiefly because the length of the stadion he used is not certainly known, so that his measurement can be made to look either remarkably close or merely respectable, depending on the conversion chosen. What matters for the moon is that the two halves of the problem were now in place: a way of finding the Earth's dimensions and a way of expressing the moon's distance in terms of them. Hipparchus, in the 2nd century before the Common Era, made the decisive advance by turning a solar eclipse into a parallax measurement. He used reports of an eclipse that had been seen as total in one region and as a partial eclipse covering something like 4/5 of the Sun at Alexandria, and from the difference in the apparent position of the moon as seen from the two places he computed how far away it must be. His figures, as they are reported in later sources, cluster in the region of 60 to 70 Earth radii, which brackets the true mean value of about 60. He was also obliged to make some assumption about the Sun's distance in order to handle the shadow cone, and he seems to have experimented with different assumptions and reported ranges rather than a single number, which is the mark of a man aware of where his uncertainties lay. Ptolemy, in the 2nd century of the Common Era, took the matter up again in the work known as the Almagest, and approached it by direct measurement rather than through eclipse reports. He observed the moon's altitude when it was near the meridian and compared its measured position with the position his lunar theory predicted for an observer at the Earth's center, attributing the discrepancy to parallax. From such comparisons, he obtained a distance at mean syzygy of about 59 Earth radii, which is within a few % of the modern value, and from the moon's apparent diameter, he derived a size that was likewise close. He then attempted to extend the method to the Sun and produced a distance far too small, an error that propagated into the accepted scale of the cosmos for well over 1,000 years, while the lunar figure stood up. Astronomers writing in Arabic and Persian from the 9th century onward repeated these determinations with instruments of greater size and graduation, refined the tables of lunar motion on which the reduction of the observations depended, and examined the assumptions in Ptolemy's procedures, in some cases pointing out inconsistencies between his lunar distances and the apparent diameters observed at eclipses. The problem was not so much that the old number was badly wrong as that the theory of the moon's motion was not good enough to separate a genuine parallax from a defect in the predicted place. Tycho Brahe, observing in the late 16th century with large graduated instruments and attending carefully to instrumental error, obtained lunar positions of unprecedented consistency, and Kepler, working over eclipse observations, noticed that the Earth's shadow measures larger than pure geometry allows, an effect that arises from the refraction and absorption of sunlight in the Earth's atmosphere, and that had quietly distorted eclipse-based estimates for centuries. The classical method reached its finest form in the middle of the 18th century, when the Moon's position was observed at the same times from Berlin in the northern hemisphere and from the Cape of Good Hope in the southern, two stations separated by a very large fraction of the Earth's diameter. The difference in the Moon's apparent place, reduced with care for refraction and for the flattening of the Earth, gave the parallax directly and with it a distance good to a fraction of 1%. From then on, the lunar distance was among the better-known quantities in astronomy, and its variation was the interesting part, since the Moon's orbit is an ellipse disturbed by the Sun, so that the distance runs from roughly 363,000 kilometers at perigee to about 405,000 at apogee, about a mean near 384,400 kilometers. In the years after the Second World War, the problem was recast as a timing problem. Radar pulses directed at the Moon were reflected and detected on their return, and the interval, together with the speed of light, gave the distance without any recourse to angles or to the Earth's radius. The round trip takes about 2.5 seconds. Radar echoes are diffuse, since they come from a broad patch of curved and rough surface, which limits the precision, and the decisive improvement came with the placing of corner cube retroreflector arrays on the lunar surface by several of the Apollo crews, and by French-built arrays carried on the Soviet Lunokhod rovers. Pulses from telescopes on Earth are returned by these arrays from a known point, and although only a very small proportion of the emitted photons come back, the accumulated timings now fix the distance to a few millimeters. Out of that long refinement come the modern figures: a lunar diameter of about 3,475 kilometers, rather more than a quarter of the Earth's, and a mean recession from the Earth of some 3.8 centimeters each year. The instrument that changed all of this arrived from a workshop rather than an observatory. In the autumn of 1608, in the Netherlands, a spectacle maker offered to the authorities a device of 2 lenses fitted in a tube that made distant things appear near. And within a few months, similar tubes were being sold in Paris, in Frankfurt, and in the Italian cities, chiefly as curiosities and as aids for watching ships and church towers from a distance. The design was simple enough that anyone with access to lenses could copy it, and the earliest examples magnified perhaps 3 or 4 times, which is roughly what a modern opera glass does. Turned on the Moon, such an instrument shows a little more than the eye alone can see, and nothing that would compel a person to rethink the heavens. The step that mattered was the making of better lenses and the patient use of them, and that step was taken in a handful of places at almost the same time. Galileo Galilei, then teaching at Padua, learned of the device in the summer of 1609 and set about grinding and polishing his own lenses, working up through a series of instruments until he had one that magnified about 20 times and, later, rather more. These were not comfortable instruments to use. The objective was a single lens of long focal length, subject to both spherical and color aberration, and the standard remedy was to mask most of its width with a ring of card or metal so that only the central portion admitted light, which sharpened the image at the cost of brightness. The field of view was very small, smaller than the moon itself, so that the observer could not take in the whole disk at once, but had to move the tube slowly across it, holding the sight of one region in memory while examining the next. The image trembled with every pulse of the hand and every gust of wind, and the eye had to be held close and still. Anything learned from such an instrument was learned by returning to it night after night. An English observer, Thomas Harriot, made a drawing of the moon in the summer of 1609, working with a low-powered tube, and the result is a modest thing: a circle with a heavy shadow line and a few blotches, the record of a man who saw that there was something there without yet being able to resolve it. He continued over the following years with better instruments and produced a series of much finer sketches, including attempts at a whole map with the principal spots in their relative places. Those drawings stayed in his papers and were not printed, so they had no influence on anyone at the time. And their interest now is that they show an independent observer arriving at the same broad conclusions from the same evidence. What Galileo saw in the closing months of that year, and described in careful order, began with the line dividing the lit from the unlit portion. On the planets and on the moon's outer edge, that boundary is smooth and regular. The inner boundary, the terminator, is not. It runs in a ragged, broken, indented line, and it moves, and its irregularities change from night to night in a way that follows the advance of the sunlight. Beyond it, in the darkness, isolated bright points appear, unconnected to the illuminated region, and over the following hours these points broaden, join one another, and are finally absorbed into the general daylight as the terminator reaches them. Within the lit region, dark patches with bright borders lie in the direction away from the sun and shorten as the sun rises over them. On Earth, the same sequence is seen at dawn from a valley floor, when the summits catch the light while the lower ground is still dark, and the shadows shorten and swing as the morning goes on. The inference was that the moon has relief, that it is uneven, rough, and full of hollows and prominences, and that its surface is not the polished sphere that the older physics of the heavens had supposed. The relief could also be measured, at least approximately. If a mountain peak is lit while the ground around it is still in shadow, then the peak stands high enough to intercept sunlight that grazes the surface at the terminator, and the distance from the peak to the terminator, together with the known size of the lunar globe, fixes the height by simple geometry. Galileo made that calculation and concluded that some lunar summits rose more than 4 miles, which was greater than the height then generally allowed for mountains on Earth. The method is sound in principle and generous in practice, because the terminator is not a clean line, and because the observer tends to misjudge the position of an isolated bright spot. So early heights came out too large. The important result was not the figure, but the fact that a height on another body had been estimated at all, from a shadow by a man at a garden window. The findings were printed in Venice in March of 1610, in a short Latin book, a slim quarto that gave the moon its account first, and then went on to the stars of the Milky Way and to the 4 attendants of Jupiter. The lunar portion carried a small set of copperplate engravings showing the moon at different phases, with the terminator broken and jagged, the Maria laid in as broad grey washes and bright specks scattered in the dark. One feature in those plates has been discussed ever since: a large round hollow sitting on the terminator with a bright rim and a shadowed floor, drawn far larger in proportion than any real formation in that part of the moon. Whether it was intended as a portrait of a particular place, or as a demonstration of what such a hollow looks like when the sun stands low over it, its effect on readers was the same. It showed a circular basin with a raised wall, seen in the one lighting condition that makes such a thing legible, and it taught a generation of observers what to look for. The same book explained the faint glow that fills the dark part of the crescent moon, the ashen light that can be seen with the unaided eye a few days from new. The explanation, which had been proposed before, is that the Earth is itself illuminated by the sun and reflects light onto the moon, so that the lunar night is lit by earthshine much as our night is lit by moonshine. Argued in print with the rest, it carried a consequence that was hard to set aside, for it made the Earth a body that shines in someone else's sky, and it placed the Earth and the moon in the same class of rough, opaque, sunlit things. Within a year, others had tubes of their own and were confirming the general picture, and the pitted moon began to appear where such things register a change of mind, including in painting, where a Roman fresco of those years set the Virgin above a lunar disk, marked with blotches and mottling, rather than the smooth crescent of earlier convention. Through the 1620s and 30s, the instruments lengthened and improved, and observers learned that a useful drawing must record the phase, since the same region is unrecognizable from one lighting to another, a crater being all rim and shadow near the terminator and nearly invisible at full moon, while a bright ray system is conspicuous at full moon and lost at low sun. In the 1630s, an engraver working in the south of France produced, for two learned patrons there, 3 plates of the moon at first quarter, full and last quarter, cut with such fidelity to the observed gradations of light that individual formations can still be identified in them. The systematic works followed in the middle of the century, when a printed map of the whole visible face appeared in the Low Countries with names attached to its features, and when an astronomer at Danzig published a large volume of lunar studies in which he described his instruments, his methods, and the slight rocking of the moon that brings a little more than half its surface into view over the course of the month, and engraved his own plates by hand. That volume set out something no single night can show: a composite of many nights in which every region has been drawn under the low sunlight that reveals its shape, assembled into one map of a world seen from a single side. Naming was the part of that mid-century work which outlasted the drawing, and it did not settle quickly. A map without names is nearly useless for correspondence between observers, since a formation can only be discussed if both parties know which one is meant, and the first attempt at a full nomenclature came from the cosmographer to the Spanish court in Brussels, whose engraved disc of 1645 carried more than 300 labels. His interest was practical before it was descriptive. He hoped that the slow advance of the sunrise line across the lunar face, measured against known features, could serve as a clock visible from any ship or any shore at the same instant, so that a navigator comparing local time with the observed moment of a crater's first illumination might read off his longitude. For that purpose, the features needed fixed and agreed names, and he supplied them from the world he lived in, dedicating the great dark plane to his king and distributing the smaller marks among cardinals, princes, saints, and a scattering of mathematicians and philosophers. That nomenclature did not survive its author's political moment, which is the ordinary fate of a naming scheme built on patronage, and of his hundreds of labels, only a handful remain in use, among them the large crater near the eastern limb, which carries the Latinized form of his own name. The map itself was more accurate than the names were durable, and it left a lesson that the next generation absorbed without quite stating it, that a system of lunar names lasts in proportion to how little it depends on the standing of particular living people. The astronomer at Danzig took the opposite route in his volume of 1647, transferring the geography of the Earth onto the Moon wholesale. He read the lunar surface as a small world with its own Mediterranean, and its own Black Sea, its own Sicily, and its own Asia Minor. And he set mountain ranges along the bright arcs where his drawings showed rows of peaks catching the light. Most of that scheme has fallen away, but the ranges kept their borrowed names, so that the curved chain along the southern edge of the largest northern plain is still the Apennines, and the ridges near it are still the Alps and the Caucasus, and the Carpathians and the Taurus. Terrestrial words attached to lunar rock for reasons that no longer apply. His nomenclature was used in some countries, and particularly in England, for many decades after his death, which meant that for a long while, two maps of the same moon could not be read against each other without a table of equivalences. The scheme that prevailed came from Bologna 4 years later, in the great astronomical compendium of a Jesuit professor there, whose colleague in the same college drew the map from telescopic observation while the professor himself supplied the names. He divided the visible disk into 8 sectors and populated each with the names of philosophers, mathematicians, and astronomers, arranged so that the ancients fell together in one region and the moderns in another, with rough regard for period and school. Ptolemy, Alphonsus, and Arzacle form a chain in the middle of the disk. Plato and Aristotle and Archimedes sit in the north. Copernicus and Kepler and Aristarchus lie in the western plains, and Galileo received a small and undistinguished mark near the western edge, a modest allotment that later observers noticed and remarked upon. The Jesuit gave his own name and his colleague's name to 2 adjoining formations near the limb where they remain. For the dark plains he chose differently, and this is the part of the scheme most people can recite without knowing its origin. He kept the old word for sea, since the plains had been taken for water since antiquity and the Latin term was already customary. But instead of terrestrial seas, he gave them conditions of weather and states of mind, so that the map acquired the sea of tranquility and the sea of serenity, the sea of clouds and the sea of rains, the sea of cold along the northern edge, the sea of moisture and the sea of vapors, the sea of fertility, the sea of nectar, the sea of crises, and the great western expanse called the ocean of storms. Smaller features took smaller words of the same kind: the Bay of Rainbows on the northwestern shore, the Marsh of Sleep, the Lake of Dreams, the Lake of Death, the Bay of Dew. The choices drew on a long tradition connecting the moon's phases with terrestrial weather and with the humours of the body, though the names were offered as a convenient vocabulary rather than as an argument about what the plains were made of. and they outlived by centuries the belief that any water lay in them. Two things gave this system its long life. One was that it could be extended without embarrassment, since new craters could be given the names of new scholars indefinitely, and each addition reinforced rather than disturbed the pattern. The other was that it was memorable, the seas in particular attaching a mood to a shape in a way that survived translation and reprinting. Through the second half of the 17th century, the Latin sea names spread through almanacs and textbooks, and by the 18th century they were general, while the ranges from Danzig persisted alongside them, so that the map in use today is a composite of two rival systems that were never reconciled so much as jointly absorbed. The measuring of the moon proceeded on its own track. A large engraved map produced at Paris towards the end of the 17th century, based on years of observation with instruments carrying measuring wires in the eyepiece, showed the near side at a size and delicacy that would not be improved on for a long time. And in the northwestern bay, the engraver worked in a small ornamental head in profile, a detail that generations of later observers looked for and found. In the middle of the following century, a mathematician at Göttingen approached the problem numerically, determining the positions of a set of lunar features by micrometric measurement and laying a coordinate grid over the disk so that any point could be given a latitude and a longitude. His chart appeared more than 10 years after his death, and though his own names for features were not taken up, his method was, because a map of the moon that is to be compared with another map must have coordinates and not only pictures. The next great advance came from a private observatory near Bremen at the end of the 18th century, where an amateur with excellent instruments published volumes of lunar topography that adopted the Bologna nomenclature, corrected it, and extended it to many features never before named. He described the narrow winding channels on the plains, and the vocabulary of clefts and reels entered the subject through his pages. The German selenographers of the following decades carried this further, and it is in their work that the labeling conventions still used were fixed, with minor craters designated by capital letters attached to the name of a larger neighbor, and hills and peaks by Greek letters, so that a crowded field could be described exactly without inventing hundreds of new personal names. A surveyor in Dresden began issuing sections of a finely measured lunar chart in the 1820s, but completed only a few of them. And two observers in Berlin, a banker with a private observatory and the astronomer who worked there, produced through the 1830s a map in 4 quadrants at a scale close to a meter for the whole disk, followed by a thick descriptive volume that catalogued and measured what the map showed. For something like 40 years, that work was the standard authority, cited whenever a position or a diameter was in question, and its authors added many names of their own, including those of natural philosophers of their own century. Later in the 1870s, the Dresden chart was completed and published by an astronomer working in Athens, who also issued a chart of his own in 25 sections recording tens of thousands of craters, and in Britain a committee of selenographers and the compilers of popular handbooks added further names as they went. By then, the inevitable had happened. Names had been duplicated, spelled differently in different countries, applied to slightly different features by different map makers, and quietly invented by observers who had not checked. The tidying took place in the early 20th century, when a collated list of lunar formations was assembled from the principal maps, and some 2 decades later, A definitive catalogue of named lunar formations was approved by the international body that had taken charge of astronomical nomenclature, fixing the spellings and the assignments that remain in force. What that catalogue preserved was, in effect, a reading list of the sciences up to the 19th century, mostly European and almost entirely male, written across a face that had been mapped from one side only, with the plains still named for rains and dreams and storms. The oceans had been telling the same story for far longer than anyone could read it. Along the shores of the Mediterranean, the rise and fall of the water is slight, a matter of a few tens of centimetres in most places, easy to overlook and easier to attribute to wind. And so the earliest written speculation on the subject came less from the inland sea than from the coasts that face the open Atlantic, where the water climbs several meters twice a day and where fishermen and traders had no choice but to learn its habits. Greek travelers who reached the ocean coasts of Europe reported back that the tides there were large, that they came twice in a day and a night, and that their size waxed and waned with the phases of the moon, and that correlation, once noticed, was never really lost again, though for many centuries it remained a correlation without a cause, filed alongside other regularities of the world that could be used without being explained. What could be used was considerable. Mariners in the medieval north kept in mind, for each harbour they visited, the age of the moon at which high water fell at noon, a quantity later called the establishment of the port, and from it they could reckon the hour of high water on any other day by adding a fixed amount for each day of the moon's age. Tables of this kind, sometimes cut into the margins of almanacs or printed as a wheel of hours around a diagram of the phases, were in circulation well before any theory of gravitation existed, and a monk writing in Northumbria in the early 8th century set down among his works on time reckoning a description of the twice-daily tides, their lag from one day to the next, and the way the same tide arrives at different hours along different stretches of the same coast. He also recorded that the tides run higher near new and full moon and lower near the quarters, which is the pattern later named for springs and neaps, springs having nothing to do with the season and neaps being an old word for scanty. Explaining any of this proved harder than tabulating it. Some medieval writers in the Islamic world and in Europe supposed the moon warmed the water and made it swell. Others imagined the moon pressing on the air, which pressed in turn upon the sea. And the difficulty in every case was that high water occurs not only when the moon is overhead, but also when it is on the opposite side of the earth, which no simple picture of attraction or pressure accounts for. In the early 17th century, Kepler wrote that the waters were drawn by the moon, in the way a magnet draws iron, an idea he could not develop quantitatively, and Galileo declined to accept it, calling such action at a distance an occult notion, and offered instead a theory in which the tides arose from the combined daily and yearly motions of the Earth, alternately hurrying and retarding the basins that held the water. He was wrong, and his own theory predicted one tide a day rather than two, which he tried to patch by appealing to the periods of oscillation of particular seas. The resolution came with the recognition that what matters is not the pull of the moon on the ocean, but the difference between the pull on the ocean and the pull on the solid earth beneath it. In the Principia of 1687, Newton showed that a body attracted according to an inverse square law is stretched along the line toward the attracting mass, because the near side is pulled harder than the center and the center harder than the far side, so that the water tends to heap up at both ends of that line at once, giving two high waters in each rotation of the Earth beneath the pair of heaps. From the same principle, he showed that the Sun raises a tide as well, smaller than the Moon's despite its far greater mass because it is so much further away, and that the two combine, reinforcing near new and full moon and partly cancelling near the quarters, which is precisely the fortnightly rhythm the harbour tables had encoded for centuries. He also understood that this static picture, an equilibrium ocean covering a smooth globe, could not predict the actual hour or height of high water in a real port, since the water has to move through channels and around continents and has natural periods of its own, and the dynamical treatment of that motion, with the ocean responding to a periodic force rather than settling under it, was developed a century later by Laplace, whose equations underlie the tidal analysis still used to compile the tables printed for every commercial harbour. The Moon's own path presented a longer and more stubborn problem. Even the earliest careful observers knew that it did not move uniformly, and Greek astronomy had accounted for the largest irregularity with an eccentric circle, while Ptolemy identified a further variation depending on the Moon's position relative to the Sun. Tycho Brahe, observing systematically before the telescope, found two more, one now called the variation, largest near the octants of the lunar month, and an annual term tied to the Earth's distance from the Sun. Alongside these went the slow turning of the line of apsides, which completes a circuit in a little under 9 years, and the backward drift of the nodes where the Moon's path crosses the ecliptic, which completes its circuit in about 18.5 years, so that any table of lunar position had to carry corrections upon corrections, each with its own period, none of them commensurate with the others. Newton attempted to derive these irregularities from gravitation and succeeded with some of them, showing how the Sun's pull distorts the Moon's orbit around the Earth, and producing an account of the motion of the nodes that matched observation reasonably well. The motion of the apsides defeated him, his calculation giving roughly half the observed rate, and the problem in general resisted closed solution because three bodies attracting one another, according to the inverse square law, do not admit the tidy answer that two bodies do. The 18th century turned this difficulty into a research program. Euler, Clairaut, and d'Alembert worked on lunar theory in parallel and in competition, submitting memoirs to prize competitions offered by the academies, and around the middle of the century, Clairaut showed that when the approximations were carried further to include terms that had been dropped as negligible, the predicted motion of the apsides doubled and agreed with the sky, which removed the last serious doubt about the sufficiency of the inverse square law. The pressure behind all this calculation was commercial and naval. Latitude at sea could be had from the Sun or the pole star with a simple instrument, but longitude required knowing the time at some reference meridian, and one way to know it was to use the Moon as the hand of a clock, measuring its angular distance from the Sun or from a bright star and comparing that distance with a table computed in advance for the reference meridian. The method was old in principle and useless in practice so long as lunar positions could not be predicted well because the Moon moves its own diameter in about an hour. So an error of 1 minute of arc in the tabulated position corresponds to roughly half a degree of longitude. Britain's Longitude Act of 1714 offered a large reward for a practicable solution, and both of the eventual solutions were pursued at once. Tobias Meyer, working in Göttingen, combined the new analytical theory with a long series of observations and produced lunar tables accurate to about a minute of arc. And those tables, refined at Greenwich, made the method of lunar distances a genuine shipboard technique. Neville Maskelyne, who had tested it on a voyage to St. Helena, established the Nautical Almanac with its first volume for the year 1767, giving the moon's distance from selected bodies at 3-hour intervals, and published instructions for the arithmetic that turned an observed distance into a time. The observation itself needed a sextant of good divided arc, 2 observers or one very practiced one, and then a computation of some length to clear the distance of the effects of refraction and parallax, which is why lunars were respected and disliked in equal measure. John Harrison's marine timekeepers, tested through the same decades, eventually offered the alternative of carrying the reference time itself, and through much of the 19th century, ships carried chronometers and checked them by occasional lunars, the two methods propping each other up rather than one simply replacing the other. Lunar theory continued to be refined long after navigators had stopped needing it so urgently. Hansen produced tables in the 1850s that served the almanacs for decades. Delaunay developed an immense analytical solution in which the moon's coordinates were expanded into series of many hundreds of terms. And toward the end of the century, Hill and then Brown built a theory whose tables, published shortly after the First World War, remained the basis of published lunar positions for something like half a century. Along the way, an old discrepancy sharpened into a discovery. Halley, comparing the timings of ancient eclipses with modern positions, concluded that the moon appeared to be gradually accelerating in its orbit, and Laplace later derived part of that acceleration from slow changes in the shape of the Earth's orbit. In the 1850s, a further analysis showed that this explanation covered only about half of the observed effect, and the remainder was eventually attributed to the tides themselves, the friction of the moving water dissipating energy, slowing the Earth's rotation and letting the moon drift very gradually outward, so that the ocean tides and the lunar orbit turned out to be two aspects of one long exchange. Photography arrived at the moon early because the moon was the only object in the night sky bright enough to make an impression on the first sensitive plates. John William Draper, working in New York around 1840, made a daguerreotype of the moon that is generally counted as the first surviving photograph of an astronomical body. And although the image was small and coarse, it showed the dark Maria and something of the Terminator, which was more than any engraving could claim as direct testimony. The difficulty was not brightness alone, but motion, since the moon drifts steadily eastward against the stars while the whole sky turns. So an exposure of any length required a telescope driven smoothly at a rate that matched the moon rather than the stars, and the early clock drives were not equal to that. There was also a subtler problem of color, because the early emulsions responded most strongly to blue and violet light, while the lenses of the period had been figured to bring yellow light to a sharp focus. So a telescope that looked perfectly sharp to the eye produced a photograph that was slightly and irreducibly soft. The first photographs that impressed astronomers as scientific documents were made at the Harvard College Observatory, where John Adams Whipple worked with the 15-inch refractor under the direction of the Bonds, and produced daguerreotypes of the moon in the years around 1850. One of them was shown at the Great Exhibition in London in 1851, where it was received as a curiosity of considerable promise, and it did prompt others to try. Warren de la Rue in England adapted a reflecting telescope with a driven mount and used the wet collodion process, whose plates were far more sensitive than the daguerreotype and allowed exposures short enough to catch the quieter moments of the air. And he went further by photographing the moon at intervals separated by weeks, so that the small rocking of libration gave him two slightly different viewpoints, which combined in a stereoscope into an image with genuine relief. Lewis Rutherford, working in New York in the 1860s, took the color problem seriously and had a lens made and corrected specifically for the photographic rays, and his lunar negatives were for some years the standard against which others were judged, sharp enough that enlargements from them were used as the basis for careful drawings. What photography changed was less the discovery of new features than the character of the record. A drawing, however skilled, passes through the memory and the judgment of the draftsman, who chooses what to keep and unconsciously tidies what he does not understand, while a plate records whatever fell on it in that fraction of a second, including things the observer had not noticed and things no one yet had a name for. Photographic atlases followed, slowly, because each required years of patient waiting for nights of good seeing at the right phase. At the Paris Observatory, Maurice Loewy and Pierre Puiseux used the Coude Equatorial, a telescope with a bent optical path that let the observer work in a fixed and comfortable room. And from the late 1890s onward, they issued the plates of a photographic atlas of the moon in installments over more than a decade, with accompanying text discussing the formations. William Henry Pickering, observing from Jamaica where the air was steady, published an atlas early in the 20th century that presented the moon at a series of phases and librations, so that the same crater could be studied under high sun and low sun, and near the limb and away from it. Photographs taken at Lick Observatory in California were enlarged and studied in Europe, and Ladislaus Weineck in Prague made large drawings from those negatives, a method that combined the fidelity of the plate with the eye's ability to integrate detail across many images. Set side by side across decades, these plates carried a negative result of some importance, which is that nothing on the moon changes. The same craters appear with the same rims and the same central peaks and the same interior ridges. The ray systems radiate along the same lines, and the boundaries of the Maria hold their shapes precisely, so that a photograph from the 1860s can be laid over one from the 1920s and matched feature for feature. There is no cloud, no veil that drifts, no seasonal darkening or brightening of the kind that had been reported for Mars, no dust obscuring a mountain range one month and clearing the next. The shadows are the other testimony. On the moon, the shadow cast by a crater wall is not merely dark, but essentially black, without the soft grey filling that scattered light produces in every terrestrial shadow, and the line of the terminator remains sharp all the way to the limb, rather than fading into a band of twilight, which is what an atmosphere of any consequence would necessarily produce. The most exacting test came from occultations. As the moon moves eastward, it passes in front of stars, and if it were surrounded by even a thin envelope of gas, the starlight grazing the limb would be refracted and dimmed for a moment before extinction, so that the star would fade rather than vanish, and its apparent position would be displaced by a measurable amount just before contact. Observers watching with good telescopes and accurate timekeeping reported that the star's disappearance was abrupt, an instantaneous cutting off with no perceptible gradation, and repeated attempts to detect the small refractive shift near the limb gave nothing beyond the errors of measurement. From this, astronomers concluded that whatever gas clings to the Moon must be present at a density smaller than the finest vacuum then achievable in a laboratory. And the same conclusion followed from the total solar eclipse, where the slender cusps of the Sun visible past the lunar limb showed no distortion of the kind an intervening atmosphere would impose. Kinetic theory supplied the reason. Once gases were understood as swarms of molecules moving at speeds that depend on temperature, and once escape velocity was understood as the threshold above which a molecule leaves and does not return, it became clear that a body's ability to hold an atmosphere depends on its gravity and its temperature together. George Johnstone Stoney set out this argument in the later 19th century, and the Moon fails the test comfortably, since its escape velocity is a little under 2.5 kilometers per second, low enough that the faster molecules of any ordinary gas at the temperatures of the sunlit surface would be lost steadily to space, and over the age of the Moon, such leakage empties any atmosphere it might once have possessed. Spectroscopy confirmed the emptiness from another direction. Sunlight reflected from the Moon shows the solar spectrum with its familiar absorption lines, together with the bands imposed by the Earth's own air through which the light has passed twice on the way to the spectrograph, and nothing else. Astronomers compared lunar spectra taken with the Moon high and low in the sky, so that the terrestrial contribution varied while any lunar contribution would not, and searched for absorption features that belonged to the Moon itself. None appeared. The reflected spectrum also proved useful in reverse, as a convenient source for studying the terrestrial bands, since it delivered sunlight that had traversed the atmosphere without the complications of looking directly at the Sun. Heat measurement developed along a parallel line and took longer because the quantity to be detected is small. Macedonio Melloni, using a thermopile behind a lens, demonstrated in the 1840s that moonlight carries a detectable warmth. And later in the century, Lawrence Parsons at Birr Castle made a long series of measurements with the great reflector there, separating the reflected sunlight from the heat radiated by the warmed surface itself, and finding that the sunlit ground reaches temperatures approaching that of boiling water. Charles Vernon Boys, with a very sensitive radio micrometer, measured the heat from different regions of the disk, and Frank Very worked through the theory of how a poorly conducting surface should warm and cool under a sun that rises and sets once a month. The decisive work came in the 1920s, when Carl Otto Lampland and William Koblenz at the Lowell Observatory, and Edison Pettit and Seth Nicholson at Mount Wilson, using a vacuum thermocouple at the focus of the 100-inch reflector, measured lunar temperatures point by point across the disk. The subsolar region, where the Sun stands overhead, was found to be well above the boiling point of water, while the unlit hemisphere fell to something in the region of 150 degrees Celsius below zero, giving a swing of more than 250 degrees between lunar noon and lunar night. During a lunar eclipse, the same instruments watched the surface pass into the Earth's shadow and recorded a temperature drop of well over 100 degrees within about an hour, and then a comparably swift recovery when the sunlight returned. Solid rock cannot cool that fast, and the rapidity implied a surface layer of very low thermal conductivity, finely divided and porous, holding almost no heat and passing almost none downward. Bernard Liet's polarimetric measurements pointed the same way, since the polarization of light reflected from the moon matched that of powdered volcanic ash rather than of smooth rock, and the photometric curve of the whole disk, which brightens sharply as full moon approaches, instead of following the gentle law of a smooth sphere, was explained by Hugo von Seeliger as the effect of countless small shadows disappearing when the sun stands directly behind the observer. Long before any spacecraft arrived, the surface was understood to be a dry, airless waste, covered in loose powder, unweathered, unstirred, and heated and chilled through each long day and night, without anything to moderate the extremes. The circular hollows that the early telescopes had revealed needed an explanation, and for close to 3 centuries the explanation was disputed, not in a single sharp confrontation, but in a long, slow, intermittent argument that changed its terms as each generation brought new evidence to it. 2 families of ideas competed. One held that the craters were built or blown out from below by volcanic forces of some kind acting on a body whose interior had once been hot, and it drew its strength from the visible resemblance between a lunar crater and a terrestrial volcanic vent, both being roughly round rings of raised ground enclosing a floor. The other held that the craters were the scars of bodies arriving from outside, striking the surface at high speed, and it drew its strength from the sheer number of the features and from their scattering across every kind of terrain, without regard to any pattern of ridges or fissures. Robert Hooke set out the problem with unusual clarity in Micrographia, published in 1665, and he did it experimentally, which was rare for the subject at the time. He dropped bullets into a soft mixture of pipe clay and water and observed that they produced round pits with raised rims, resembling in miniature what the telescope showed on the moon. He also heated alabaster powder until it boiled, and watched the bursting of bubbles leave behind circular hollows with central mounds, which resembled the lunar craters just as well. Between the 2 analogies, he chose the second, and his reason was a reasonable one for his century, since he could see no source in the heavens for the great numbers of falling bodies that the first explanation would require. Space, as then understood, was not populated with debris. For the next century and a half, the volcanic view held the field with little serious challenge. William Herschel, observing in the 1780s, reported what he took to be eruptions glowing on the unlit portion of the disk, a report now generally understood as bright cratered ground catching earthshine or sunlight near the terminator, and his authority carried weight. Johann Hieronymus Schröter, whose detailed selenographic work belongs to the closing years of the 18th century, introduced the word crater into lunar description precisely because of its volcanic associations, and the terminology quietly carried the theory along with it. When Wilhelm Beer and Johann Heinrich Mädler produced their careful map in the 1830s, the features were described in language that assumed an internal origin, and the assumption became a habit of thought. Dissenting voices existed. Franz von Paula Gruithuisen argued in the early 19th century that the craters were the marks of impacts, and Richard Anthony Proctor writing in the 1870s, made the meteoric case at length for a general readership. The difficulty these advocates faced was mechanical rather than observational. Bodies arriving from space would come in at all angles, mostly obliquely, and an oblique blow ought to gouge an elongated trench rather than a circle. Yet the lunar craters are almost all circular, and the few elliptical ones are rare enough to look like exceptions. Until that objection was answered, the impact hypothesis could be dismissed as inconsistent with the very evidence it claimed to explain. The most thorough 19th century treatment came from Grove Carl Gilbert, a geologist trained in the field rather than at the telescope, who spent time observing the moon at the Naval Observatory in Washington and set out his conclusions in the 1890s. Gilbert measured and reasoned like a geologist. He noted that the volume of material heaped in a crater's rim corresponds roughly to the volume missing from its cavity, which is what excavation would produce and what an eruption from depth would not. And he noted that lunar craters are shallow sources rather than the tall cones that terrestrial volcanoes build. He threw balls of clay into beds of clay to study the resulting forms. He also traced a system of long radial gouges spreading outward from the Mare Imbrium basin, features he called the Imbrium sculpture, and interpreted them as the marks of debris thrown out from one enormous collision. He could not solve the problem of circularity, and he acknowledged it. Gilbert had also examined a great pit in northern Arizona, then called Coon Butte, and had looked for the buried mass of iron that an impact should have left. Finding no such mass and no magnetic anomaly, he concluded that the pit had been formed by a subterranean steam explosion, and in that particular judgment he was mistaken. Daniel Barringer, from the first years of the 20th century, argued the impact case for the same crater and spent years drilling in search of the iron body, which was never found in the form he expected. The resolution came only later, with the understanding that a body arriving at tens of kilometers per second does not survive burial as a lump, because the kinetic energy it carries is comparable to that of an equivalent mass of high explosive, and it is largely vaporized at the moment of contact. That insight, developed in the 1920s by the New Zealand astronomer Algernon Charles Gifford, dissolved the circularity objection as well. If the projectile is destroyed almost instantly and its energy released in a small volume near the surface, the resulting excavation is governed by the explosion rather than by the direction of arrival, and it will be round whatever the angle of the incoming path, provided the path is not very nearly grazing. In the same decade, Alfred Wegener, better known for his work on continental drift, published a study of lunar craters in which he fired and dropped material into fine cement powder and produced circular pits with central peaks and bright radial streaks, resembling the ray systems around Tycho and Copernicus. The quantitative argument arrived with Ralph Baldwin, whose book On the Face of the Moon appeared in 1949. Baldwin plotted the depth of craters against their diameter, using lunar measurements together with terrestrial explosion craters, including the pits left by bombs and by large charges, and found that the points fell along a single continuous relation extending over a great range of sizes. Volcanic vents did not lie on that line. Explosion craters and lunar craters did. Harold Urey, working through the chemistry and physics of the planets in the following years, argued the impact case from a different direction, and by the 1950s, the balance of professional opinion had shifted, though not completely, and some geologists continued to press for internal origins well into the following decade. 2 further lines of terrestrial work closed the case. Eugene Shoemaker mapped the Arizona crater in structural detail and compared it with the craters produced by nuclear explosions at the Nevada test site, showing that both share the same distinctive architecture, including a rim of strata folded back on themselves so that the layers lie in inverted order, an arrangement produced by rapid excavation and by nothing that rises from below. And in 1960, the mineral coesite, a dense form of silica that forms only under pressures far beyond anything volcanic processes generate at the surface, was identified in the sandstone of the Arizona crater, giving a diagnostic signature of shock. The following year, the same signature was found in the rocks of the Riez Basin in southern Germany. A large structure that had long been read as volcanic, and its reinterpretation as an impact site showed how easily the 2 origins had been confused on Earth. Meanwhile, the craters themselves were being counted. Their sizes follow a smooth distribution, with small ones far outnumbering large ones in a proportion resembling the population of small bodies known to orbit the Sun, and their positions are scattered, essentially at random, rather than aligned along fractures as volcanic vents on Earth tend to be. Shoemaker and Robert Hackman used the fact that older surfaces accumulate more craters to build a relative timescale for the Moon. Recognizing that the dark Maria, sparsely cratered, must be younger than the crowded highlands, and that the ejecta blanket of a basin must be younger than what it covers. Crater counting became the working chronology of lunar geology before any sample had been returned. Volcanism was not banished from the Moon by any of this. The Maria are floods of basalt, genuinely volcanic in origin, and there are small, dark haloed vents, sinuous channels cut by flowing lava, and low domes that belong to the same family of processes. Acclaimed spectroscopic detection of gas within the crater Alphonsus, reported in the late 1950s, kept the question of present-day activity alive for a time. What the long argument settled was narrower and firmer. The circular craters that dominate the lunar landscape, from basins hundreds of kilometers across down to pits too small to resolve from Earth, were made by things falling out of the sky. For all the ingenuity of the crater argument, it had been conducted at a distance of roughly 380,000 kilometers, with the same hemisphere permanently turned towards the observer and never a single point of the surface examined from closer than the top of the atmosphere. 2 things remained genuinely unknown. One was the appearance of the far side, hidden by the Moon's synchronous rotation and never glimpsed except for the narrow slivers that libration swings briefly into view around the limb. The other was the texture of the ground itself at the scale of a footstep, which mattered because some respected estimates held that the surface might be covered in a deep layer of loose, electrostatically fluffed dust, into which any arriving object would sink without trace. Both questions were beyond the reach of telescopes, and both were answered within a single decade by machines. The first attempts were mostly failures, as early rocketry generally was. A series of American probes launched in 1958 either exploded, fell back, or fell short. In January 1959, the Soviet spacecraft later called Luna 1 passed the Moon at a distance of several thousand kilometers, missing its target but becoming the first object to leave the vicinity of the Earth entirely, and carrying instruments that registered a steady stream of charged particles in interplanetary space. An early direct measurement of what came to be called the solar wind. In March of that year, an American probe, Pioneer 4, also flew past, further off than intended. Then in September 1959, Luna 2 struck the Moon east of Mare Serenitatis, the first human artifact to reach another body, and its magnetometer, passing close to the surface, found no magnetic field of any appreciable strength and no belt of trapped radiation, which was a real result and not merely a symbolic one. 3 weeks later came the mission that mattered most for the map. Luna 3 was launched in early October 1959 on a trajectory that carried it around the far side while the Sun stood behind the spacecraft, so that the hidden hemisphere was fully illuminated. Its camera used photographic film, developed and fixed on board by an automatic processor, and the dried negatives were then scanned by a flying spot of light, and the varying brightness transmitted as a facsimile signal, a technique borrowed from the transmission of newspaper photographs. The pictures that arrived on Earth were few, coarse, streaked with noise, and difficult to interpret, and yet they carried an unmistakable message. The far side was not a mirror of the near side. It had no broad, dark plains comparable to Oceanus Procellarum or Mare Imbrium, only a crowded, bright, heavily cratered surface with a very few small, dark patches. The asymmetry was immediate and unexplained, and it has remained one of the central facts of lunar science. Names followed the photographs. Soviet astronomers prepared an atlas from the Luna 3 frames and proposed designations for the features they believed they could identify. And the International Astronomical Union took up the question in the early 1960s, which is why the far side carries a dark flawed crater named for Tsiolkovsky, the theorist of rocket flight, and a small mare named Moscoviense, the Sea of Moscow, admitted into a nomenclature that had until then been strictly the property of the 17th century. One other supposed sea, given a name meaning the Sea of Dreams, turned out on better imaging to be an assemblage of separate features rather than a single plane, and quietly left the maps. In 1965, the probe Zond 3 photographed a further portion of the far side, including regions the earlier mission had missed, and did so with markedly better optics, so that within 6 years of the first glimpse, the outline of the entire globe was known in at least a rough way. The Americans approached the problem from the other end, aiming not for the hidden hemisphere but for close-range detail on the near side, and their Ranger spacecraft were built to send television pictures continuously during a deliberate final plunge, gaining resolution until the moment of destruction. The program's early history was a catalogue of disappointments, with launch failures, lost attitude control, a probe that reached the far side but sent nothing back, and in February 1964, a spacecraft that arrived precisely on target in Mare Tranquillitatis with cameras that never switched on. Ranger 7, in July 1964, worked. Over the last quarter of an hour of its flight, it returned several thousand images of a mare surface near the crater Guernica, each one covering a smaller area than the last, and the final frames resolved objects less than a meter across. What they showed was a landscape rounded and softened at every scale, pitted with craters down to the limit of the pictures, with no smooth patch anywhere, and no sign of a threshold below which cratering stopped. Ranger 8 repeated the performance in Mare Tranquillitatis in February 1965, and Ranger 9, the following month, fell into the floor of Alphonsus, the crater with the suspected gas emission, and its pictures were broadcast live on American television as they came in, so that the approach was watched by an audience while it happened. None of this settled the question of bearing strength, since a dust layer soft enough to swallow a lander would look no different from a firm one in a photograph taken from above. That question was answered on the 3rd of February 1966, when Luna 9 reached Oceanus Procellarum, slowed with a retro-rocket, and ejected a sealed spherical capsule cushioned by inflatable bags, which bounced, came to rest, opened 4 petal-like covers to right itself, and began scanning a panorama with a small mirror camera. The resulting pictures showed a level plane of fine granular material strewn with small stones, sharply lit, with a horizon a short distance away, and they showed the capsule sitting on the surface rather than sinking into it. The signals were in a standard facsimile format, and radio astronomers at Jodrell Bank in England, following the transmission, recognized the format and produced prints of their own, which appeared in the newspapers slightly ahead of the official Soviet release. Later that year, Luna 13 landed in the same general region, carrying a small penetrometer and a radiation density gauge, which pressed and probed the regolith directly and returned an estimate of its density and mechanical resistance, comparable to that of a moderately compacted terrestrial soil. 2 months after Luna 9, Luna 10 was placed in orbit around the Moon, the first artificial satellite of another body, and its gamma-ray instrument made a first crude survey of the composition of the surface, indicating rocks broadly of basaltic character rather than the granitic material common in Earth's continental crust. Then in June 1966, the first of the American Surveyor landers set down, also in Oceanus Procellarum, near the ghost crater Flamsteed, and worked for weeks, returning many thousands of photographs of the ground around its footpads, the pads themselves pressed shallowly into the soil, the fine material clumping slightly where it had been disturbed. Later, surveyors carried a scoop that dug trenches and tested the cohesion of the regolith, and an alpha-scattering instrument that bombarded the soil and analyzed the returning particles to give a chemical composition. The Mare sites showed abundant iron, calcium, and titanium in proportions consistent with basalt. The final spacecraft of the series landed in January 1968 on the rugged, bright ejecta north of Tycho in the Highlands, and its analysis returned a distinctly different result. With less iron and more aluminium, the first direct chemical confirmation that the pale highlands and the dark plains are made of different rock. Overlapping with the landers, 5 lunar orbiter spacecraft circled the Moon between 1966 and 1967, carrying the same essential trick as Luna 3 but refined. Film exposed in 2 focal lengths, developed on board against a moist processing web, then scanned line by line and transmitted, the strips reassembled on Earth into large mosaics whose faint seams are still visible in the prints. The first missions concentrated on candidate landing sites along the equator, and the last 2 swept the whole globe, so that by the end of the program, almost the entire surface, including the far side, had been photographed well enough to map. Among the results was a clear view of the Oriental Basin on the western limb, its concentric rings visible for the first time as a complete structure, and from the careful tracking of the spacecraft radio signals, the discovery that the great circular maria sit above concentrations of excess mass, dense enough to tug a passing satellite measurably out of its path. The first samples came back in a pair of sealed aluminium boxes in July 1969. About 20 kilograms of rock and soil collected in a little over 2 hours of walking near the southwestern edge of Mare Tranquillitatis. And over the following 3.5 years, 5 more landings added to the collection, until the 6 Apollo missions together had returned something on the order of 380 kilograms of material from 6 widely separated sites. Alongside them, 3 Soviet robotic spacecraft, Luna 16, 20 and 24, drilled into the surface and lifted small cores back to Earth, a few hundred grams in total, but drawn from places no crew had visited, including the deep core recovered from Mare Crisium. The rocks were catalogued, sawn, photographed, and distributed to laboratories in many countries. And most of the mass is still held in curated storage, some of it never opened. What the laboratories found was, in its broad outline, what the surveyor analyses had suggested, and in its detail, something no remote measurement could have given. The dark plains were made of basalt, a volcanic rock familiar in substance from terrestrial lava flows, though richer in iron and in some samples remarkably rich in titanium, and it had solidified from melt that was extremely dry. There were no clays, no micas, no hydrated minerals of the sort that form wherever water touches rock on Earth, and no trace of the rust and weathering products that dominate terrestrial soils. Volatile elements were depleted, while refractory elements were relatively enriched. Iron appeared in metallic form as small grains, which on Earth would have oxidized long before, and the ratios of the stable isotopes of oxygen, measured with great care, turned out to be almost indistinguishable from those of Earth's mantle, a similarity that would eventually shape every argument about how the Moon came to exist. The Pale Highlands, sampled at Apollo 16 in the Descartes region and along the Apennine front at Apollo 15, were dominated by anorthosite, a rock composed largely of calcium-rich plagioclase feldspar, pale and coarse, and by breccias, which are fragments of older rock broken and welded together by impact, sometimes in several generations, so that a single-hand specimen might contain within it the shattered pieces of an earlier breccia. Radiometric dating, using the decay of rubidium to strontium and of potassium to argon and refined by the argon-argon method, gave the Mare basalts ages between roughly 3 and a bit and 3.8 billion years, while the highland rocks came out consistently older, clustering near 4.4 billion years and in places approaching the age of the solar system itself. That difference in age, coupled with the abundance of feldspar in the highlands, supported a picture in which the outer part of the young moon was largely molten, a global layer of magma in which plagioclase, being less dense than the melt, floated upward to accumulate as a thick crust of anorthosite, while heavier minerals rich in iron and magnesium settled beneath it. The last liquid to crystallize, squeezed between the two, was enriched in potassium, in the rare earth elements and in phosphorus, and that residual composition, abbreviated by geochemists to a short pronounceable label, turns up in samples from several sites and appears from later orbital mapping to be concentrated on the near side. Many of the highland breccias record intense impact heating at around 3.9 billion years, which some read as evidence for a spike in bombardment and others as an artifact of where the landings happened to be. The loose surface layer, the regolith, proved to be its own subject. It is a few meters deep on the Maria and thicker on the older highlands, produced by billions of years of impacts grinding rock into powder, and it contains, besides mineral fragments, small glass spheres and irregular droplets formed in impact melts, and a peculiar welded aggregate of glass and grains called agglutinate that accumulates the longer a soil sits exposed. The grains carry microscopic pits from micrometeorite strikes, and in their outermost skins, atoms of hydrogen, helium, and other gases implanted directly from the solar wind. Because cosmic rays produce measurable isotopes in exposed material, individual samples could be assigned an exposure age, distinct from their crystallization age, telling how long each had lain near the surface. The orange soil found at the rim of Shorty Crater during the last mission turned out to be glass beads of volcanic origin, not the recent oxidation some had briefly suspected. The instruments left behind gathered a different kind of information, over years rather than in a few hours. Each of the later landings deployed a set of experiments powered by a radioisotope generator, connected by ribbon cables to a central station that relayed data to Earth, and the network continued transmitting long after the last crew had gone, until the stations were switched off in the autumn of 1977. Among the instruments were seismometers sensitive enough to register the footsteps of the astronauts walking away from them, magnetometers, detectors of the thin gas above the surface, solar wind monitors, and at 2 sites probes emplaced in drilled holes to measure the heat flowing outward from the interior. The seismic record was unlike anything from terrestrial stations. A moderate impact or quake set the moon vibrating for an hour or more, the signal rising slowly and decaying slowly because the outer crust is fractured, dry, and almost free of the water and heat that damp vibrations on Earth. So seismic energy scatters rather than being absorbed. 4 classes of event were distinguished: meteoroid impacts, small shallow quakes, thermal cracking of the surface at sunrise and sunset, and deep quakes originating some 700 to 1,000 kilometers down and recurring with the rhythm of the moon's orbit, tidally triggered. To supply signals of known time and place, spent rocket stages and discarded lunar module ascent stages were deliberately crashed into the surface. And from those, together with natural events, the layering beneath the landing sites was worked out. A crust some tens of kilometers thick, thinner under the Maria and thicker on the far side, above a mantle largely solid and seismically quiet, with a zone of partial melt near its base, and from later reanalysis of the same tapes, indications of a small dense core a few hundred kilometers in radius. The magnetometers found no global field of consequence, only weak and patchy magnetization. Yet many of the returned rocks carried a stable remnant magnetization acquired as they cooled, which is difficult to explain unless the young moon once generated a field of its own from a circulating molten core that has since gone quiet. The heat flow probes measured an outward flux modest in absolute terms, but larger than some had expected for so small a body. consistent with a crust enriched in the radioactive elements uranium, thorium, and potassium. 3 of the landings also left a passive device that required no power and no maintenance. A panel of fused silica corner cubes, each shaped so that light entering it returns along the direction it came from, whatever the angle of arrival. 2 more such reflectors, built in France, traveled aboard the Lunokhod rovers. Observatories on Earth fire brief laser pulses at these panels and time the return of the handful of photons that survive the round trip, a journey of about 2.5 seconds. From the arrival times, averaged over many pulses and corrected for the atmosphere, the distance to a fixed point on the Moon can be recovered first to within tens of centimeters, and now, with improved lasers and detectors, to within a few millimeters, and the reflectors continue to be used well over half a century after the first was set down. Decades of such measurements have made the Moon's slow retreat a matter of routine observation. The Moon raises tidal bulges in the oceans and in the solid Earth, and because Earth rotates faster than the Moon orbits, friction drags those bulges slightly ahead of the line joining the 2 bodies, so their gravitational pull tugs the Moon forward along its path, lifting it into a wider orbit while draining angular momentum from Earth's spin. The measured rate is close to 3.8 centimeters a year, and the corresponding lengthening of the day is small enough that it is best detected by comparing modern clocks with the timings of ancient eclipses and by counting the fine growth layers preserved in some fossil shells and tidal sediments, which suggest that in the distant past the day was shorter and the month contained more of them. Because the retreat can be measured, it can also be run backwards, and the arithmetic of that reversal is one of the reasons the question of the Moon's origin has never been a purely speculative one. If the present rate is projected into the deep past, it implies a Moon that was once far closer, raising tides of a scale no coastline records. And although the simple projection cannot be trusted across billions of years, since the rate depends on the shapes of ocean basins and the distribution of continents, and has certainly varied, the general direction is not in doubt. The Moon began near, and it has been moving away ever since, and any account of how it came to exist has to begin with a body close to Earth, hot, and sharing Earth's motion. The oldest of the modern explanations was proposed in the late 19th century by George Darwin, who considered the consequences of tidal friction acting over immense stretches of time and suggested that Earth had once spun so rapidly that it became unstable and shed a great mass of material from its equator, which then coalesced into the Moon and drifted outward. For a while it was popular to identify the scar of that separation with the basin of the Pacific, an idea that dissolved once the age and mobility of the ocean floor were understood, and the deeper difficulty was mechanical. The combined spin of the present Earth and the orbital motion of the Moon do not add up to enough rotation to have brought an early Earth anywhere near the point of breakup, and no plausible way was found to remove the excess. A second family of explanations held that the Moon formed elsewhere in the inner solar system as an independent small planet and was later captured by Earth during a close passage. Capture is not impossible in principle, but it requires that a great deal of energy be removed from the encounter at exactly the right moment by an extended atmosphere or by tidal dissipation or by a third body, and the range of approach speeds and geometries that lead to a stable bound orbit rather than a collision or an escape, is narrow. The hypothesis had the attraction of explaining why the Moon differs from Earth in some respects, and it lost ground as it became clear how closely the two bodies resemble each other in other respects. The third proposal, sometimes called co-accretion or the sister planet model, had the Moon growing in orbit around Earth from the same swarm of small bodies that built the planet at the same time and from the same material. This accounted well for the chemical family resemblance, and it accounted poorly for two things that eventually proved decisive. The Moon's mean density is much lower than Earth's. Its iron core is small in proportion to its size, and it is markedly depleted in the metals that sink into a planetary core, which is difficult to arrange if both bodies were assembled from the same well-mixed reservoir. And the angular momentum of the Earth and Moon system, considered as a whole, is larger than a quiet accumulation of small pieces would be expected to leave behind. The returned samples sharpened all of these constraints. They showed a body poor in iron, poor in the volatile elements that boil away easily, essentially devoid of water in the minerals as first analyzed, and covered in an ancient crust of feldspar-rich rock that is most easily explained by a global magma ocean in which light minerals floated to the top and solidified as the highlands. They also showed oxygen isotope ratios that matched terrestrial rocks to a precision that set the Moon apart from the meteorites believed to come from Mars or from the asteroid belt, each of which carries its own distinct signature. Whatever the Moon was made of, it was made largely of the same stock as Earth, and it was made hot, and it was made without much of an iron core. The explanation that came to fit those facts was put forward in the middle of the 1970s by two separate groups working on the mechanics of planet formation, and it holds that late in Earth's assembly, the growing planet was struck a glancing blow by another body roughly the size of Mars, which is often given the name Theia. In this account, the impactor's core sank and merged with Earth's, while a mixture of mantle rock from both bodies was thrown out in a hot disk of vapor and melt, from which the Moon assembled rapidly, perhaps within a few years or decades, above the level at which tides would have torn it apart. The idea gained force through the 1980s and 90s as computers became capable of following the collision numerically, and the simulations reproduced the large angular momentum, the iron-poor composition, the absence of volatiles, and the initial molten state, which no earlier hypothesis had managed together. The difficulty that remains is a matter of degree rather than direction. As isotopic measurements grew more precise, the Moon's similarity to Earth extended beyond oxygen to titanium, chromium, and other elements, and the match is closer than most simulations of a glancing impact predict, since those simulations tend to build the Moon mainly from the impactor, which would have carried its own isotopic signature unless it happened to form at very nearly the same distance from the Sun. Several adjustments have been explored, an impactor of composition unusually close to Earth's, a more energetic collision onto an already rapidly spinning Earth that draws more material from the terrestrial mantle, a phase in which the two bodies vaporize into a single extended structure, sometimes called a synestia, within which the isotopes mix thoroughly before the Moon condenses, and, in another line of work, a series of smaller impacts, each producing a moonlet that later merged. The debate concerns the details of the collision rather than whether a collision occurred, and it is pursued through laboratory isotope work on the samples, through models of vapor exchange between disk and planet, and through improved simulation. Timing has been approached through the radioactive clocks in the lunar rocks and in the oldest terrestrial minerals, and through the decay of short-lived isotopes that were still present when the solar system was young, and that record how quickly metal separated from rock. The results place the event within roughly the first 100 million years of solar system history, and the crust that solidified from the magma ocean survives in the highlands as some of the oldest rock accessible to any laboratory. After that, the record is one of slow cooling, heavy bombardment fading, mere volcanism filling the Great Basins and then ceasing, the interior contracting and the crust wrinkling into small thrust faults and scarps that orbiting cameras have now catalogued in large numbers. Some of them apparently young enough that the shallow moonquakes recorded by the surface seismometers may be related to their movement. The Moon's axis is tilted only slightly with respect to its orbit, and this has a consequence at the poles. There are depressions there, the floors of craters and the shadows of their walls, where sunlight has not reached for a very long time and where surface temperatures remain among the lowest measured anywhere in the inner solar system. Such places act as traps for anything volatile that wanders in. A neutron spectrometer carried by an orbiter in the late 1990s found an excess of hydrogen concentrated near both poles, consistent with buried ice, and later missions added to the case. An instrument on an Indian orbiter mapped absorption features associated with water and hydroxyl across parts of the surface. A spacecraft was deliberately steered into a shadowed polar crater so that the ejected plume could be examined for water vapor, and orbiting ultraviolet and infrared instruments have found surface frost patches within the darkest terrain. The ice appears to be uneven, mixed through the regolith rather than lying as a clean sheet, and its likely sources include comet and asteroid impacts, along with hydrogen from the solar wind combining with oxygen in the soil. Mapping continues at a level of detail that has no parallel for any body other than Earth. A long-lived orbiter has built global topography from laser altimetry and imaged much of the surface at meter-scale resolution. A pair of spacecraft flying in formation measured the gravity field with enough precision to reveal variations in crustal thickness, including the persistent difference between the thin near side and the thicker far side. Japanese, Chinese, and Indian missions have added imaging, mineral maps, and, more recently, samples returned from the near side and from the far side. Names are still being added to the standard lists by the international body that governs them, following the conventions settled centuries ago, and the maps now include the shadow calendars of the polar craters, computed hour by hour, for a surface whose broad history is understood and whose beginning is still being argued over in the fine print. We are going to stop here. The music will carry on for a while and then it will fade on its own. There is nothing more to do tonight. Rest well and see you very soon.